I will give one more example of principle of entropy compensation in use, and that has to do with biochemical synthesis. So these are biological processes involved in the synthesis of macromolecules. One good example is the reaction of glucose, which has a 6 carbon ring. We can call this ring type A. This reacts with fructose, which is another 6 carbon ring of type B, and the end product is sucrose, which is 6 carbon 6 carbon bond plus water. And this reaction occurs at constant temperature and pressure. So we need to check the change in the Gibbs free energy, total Gibbs free energy, to see which direction the reaction will proceed thermodynamically. So if we have 1 mole of each constituent, so we're going to have as a result 1 mole of each constituent being produced in the reaction. And if you look at from left to right, the change in the Gibbs free energy delta G is plus 0.24 electron volts per mole. And because the Gibbs free energy is positive, this implies that the reaction proceeds from right to left. So we see the dissociation of sucrose reacting with water to produce glucose and fructose. Now, if the aim of this reaction is to produce sucrose synthesis, we need an auxiliary reaction. As you remember, in the second law of thermodynamics tells us that the total entropy change must be greater or equal to 0, which implies that the Gibbs free energy should be minimized. So delta G should be less or equal to 0. So that means in order to achieve sucrose synthesis, we need to have an auxiliary reaction. So this requires that we have an auxiliary reaction which has a change in the Gibbs free energy negative, such that the total change in the Gibbs free energy will be less or equal to 0. So this is going to have delta G prime that is going to make sure that the total Gibbs free energy change delta G plus delta G prime will be less or equal to 0. So in biological organisms, this auxiliary reaction involves adenosine triphosphate, ATP. So in biological organisms, we have the following auxiliary reaction. ATP plus water produces ADP, adenosine diphosphate, plus a phosphate. And if you look at the change in the Gibbs free energy for this reaction is minus 0.3 electron volts. And then if these two reactions occur at the same time, we have delta G plus delta G prime will be plus 0.24 minus 0.30 minus 0.06 electron volt per mole of the constituents. So we need to combine these two reactions, a common intermediate glucose 1-phosphate can be used. So to combine the two reactions, we can use glucose 1-phosphate intermediate product, glucose 1-phosphate is used. So how does that work? Well, we have the presence of enzymes in the presence of catalysts, reaction catalysts or enzymes. Adenosine 3-phosphate will react with glucose to produce adenosine diphosphate plus glucose 1-phosphate. So on the other hand, this glucose 1-phosphate will react with fructose to produce sucrose plus a phosphate. So the end reaction can be described as follows: adenosine 3-phosphate reacting with glucose and fructose to produce sucrose plus ADP plus a phosphate. So this reaction is feasible because delta G total, delta G star, is less than 0. Similarly, if you think about other biological macromolecule syntheses, that's the same way nucleic acids can produce DNA, or amino acids can produce proteins. So basically what makes life possible is the fact that we have this principle of entropy compensation. If we have a process that is going to produce a more ordered macromolecule at the end of the biochemical synthesis, we must have auxiliary reactions that makes sure that the overall change in the Gibbs free energy is negative, or basically equivalently the total entropy of the universe is increasing. So we have seen one example: glucose and fructose reacting to produce sucrose, an ordered biological macromolecule that involves a total change in the Gibbs free energy of plus 0.24 electron volts per mole. So naturally this reaction will proceed from right to left, but by introducing an auxiliary reaction where we have adenosine 3-phosphate reacting with water to produce ADP plus a phosphate, where the Gibbs free energy change is minus 0.3 electron volts, with the help of catalysts and enzymes, ATP reacting with glucose to produce a glucose 1-phosphate intermediate product, and that intermediate product reacting with fructose to produce sucrose and phosphate. Basically we have the overall reaction ATP plus glucose plus fructose producing synthesizing sucrose, ADP and a phosphate. The total change in the Gibbs free energy is negative, therefore this reaction proceeds to the right. And similarly, the production of the synthesis of DNA and proteins, from nucleic acids to DNA and amino acids to proteins, proceeds exactly the same way, using the principle of entropy compensation with the aid of auxiliary reactions.